Here is a second example. So we want to find the volume of a solid bounded by the planes y equals 0, y plus z equals 3, and the cylinder x squared plus z squared equals 4. So this problem is very similar to the one that we did in class, but now the orientation is completely different because now the orientation of the volume is not on the z-axis, now we have it on the y-axis. So first, let's start off by drawing the picture because we don't know what exactly we're integrating. So we're going to start off by drawing our xyz plane. Here's our x, our y, and our z. And notice here that we have this particular plane. So we start off with y equals 0. Okay, well, y equals 0 is just basically the xz plane. So we're starting there. So you can kind of think about as this being the wall. Okay, so it cannot go anything further. So I'm either going to be in the negative side or in the positive side. And that's kind of confirmed by this plane. So this plane y plus z equals 3. This is the plane. And a way to draw kind of the plane is just to kind of try to think about the x and the y intercepts. In this case, it will be z and y. So let's think of the y intercept. So that will happen when z equals 0. So what we're going to get is y plus 0 equals 3. So y equals 3. So at y, we're going to go all the way to 3. And then we're going to look at the z-intercept. So where it crosses the z-axis. So we're going to let y equal 0. Okay, so then what we're going to get is 0 plus z equals 3. We get exactly the same thing. So let's just say z equals 3 is up here. So z equals 3. So if you can kind of think about this in the yz plane, you can see that it's just basically a line that's connecting there. A line that's passing through. Okay. So that's basically what this plane would look like. Obviously, it would extend across the x-axis because x is free. I'll try to draw it a little bit nicer in a second. So imagine that this guy is just going inside of it, side of the wall, right, and also over. Okay, so it's just a sheet of paper going right, slicing right through these 2 points. And now what we have this cylinder. So this cylinder is just x squared plus z squared equals 4. So that means that we have a circle. This guy is still a circle, but in this case, it's of radius 4 on the xz plane. So notice that this guy is on the xz plane. Okay, so on the xz plane, we're just looking at this plane now. And we have a circle of radius 2. So we can kind of think about it this way. And then out this way. And then going inside of the page this way. Okay, so there's my cylinder. Now, in this case, because I'm looking at the volume bounded by the planes, okay, so we're starting at y equals 0. And then our stopping point in this case would be all the way to the plane y plus z equals 3. So we're going to keep going until we reach this plane. Okay, at that particular point. Okay, so we can kind of think about this as this region. Okay, so if you kind of think about this region looking like this, try my best to draw this. Okay, we're basically looking at this particular soda can that we kind of broke through. And we're looking at all the volume that's bounded inside of it. So all of this volume that's inside of the soda can. You kind of think about it this way. Okay, and remember that this line is just a plane. So if you want me to draw a little bit the plane a little bit better, imagine that you kind of have this sheet of paper. You're right, this is just a plane. Okay, so this is basically what the shape should somewhat look like. Okay, and now we want to find the volume of all this guy. So this guy is just going to be a double integral because that's how we will find the volume over the region R. Right now we're not sure what R it would be, but you can see that this is just going to be an upper minus lower problem. Okay, so we're going to take the double integral over the region. Notice that if I were to look at the upper function, my upper function clearly, if I'm going in the y direction here, the figure is oriented on the y-axis. So this is oriented on the y. It's no longer on the z. So imagine that we have an arrow pointing or coming from the negative y-axis all the way into the graph, into this volume. So what's going to happen is that I'm slicing through the first plane, which is y equals 0, okay, all the way to the very top, which is going to be this plane. So the last graph that it hits is actually this plane, okay? So let me just draw it like this. This is the last graph that it's hitting. This is where it's stopping. So my upper graph in this case is going to be the plane, whatever the equation of the plane is, minus my lower function. Well, it's crossed through y equals 0, so it'll be 0. I'm going to write dA for now. So now notice that because we're going on the y-axis, we need to have everything to have y equals. Okay, so notice how it started from this lower plane at y equals 0 all the way to this upper plane. So what would this plane be in terms of y? Well, since we know that y plus z equals 3, I would subtract the z over and we'll get y equals 3 minus z. So that means that this guy is going to be the double integral over the region. The plane itself is going to be y equals 3 minus z, and then minus 0, dA. Now in this case, dA, notice that this is in terms, my function inside is in terms of f of x and z, okay? So now we have y equaling a function of x and z. X is not here because x can be free. So that means since everything is on the y-axis, that means the thing that we have to integrate over, our region, is going to be on the xz axis. So what we have is dz dx, or it can be dx dz, depending on the region. Okay? Now, the question here is, what is going to be my r? Okay? So my r is going to be whatever is projected on the xz plane. And you can see that the picture that's projected on the xz plane is going to be this circle. So in this circle comes from this cylinder that we projected. So the cylinder, x squared plus z squared equals 4, is going to be the projection of the region R. Okay? So you're going to have this guy. So circle of radius 2. And now in this case, it would be easier to convert everything to polar coordinates. Now we have to be very careful because we're oriented on the y-axis, our polar coordinates are a little bit all messed up now. So x in this case is still r cosine of theta. That one still hasn't changed. But notice how we're not on the xy plane anymore. We're on the xz plane. So now the y itself, whoops, I wrote y. We're on the xz plane. Now our y is no longer going to be our y. Now we have a z. So z is going to take into account everything that y was. And y was r sine of theta. So now we have a new type of coordinate system. But now instead of the y, we're just substituting the y with the z. Okay? So now we're going to have the double integral. This is going to be 3 minus z, which is r sine theta. My dz or my dA is going to be r dr d theta. Let me put this in parentheses. And now we got to think about what r is. So r is going to be the distance from the pole all the way to whatever the shape is. So in this case, this shape is just r equals 2, right? Because it has a circle of radius 2. So it goes from 0 to 2. That's going to be r. And now my angle theta, well, that one's just easy because we're looking at all of the entire circle. It doesn't tell us any restrictions on the problem that is in the first octant or anything like that. So we're going to go and take the whole circle, 0 to 2 pi. And now all we have to do is just integrate it. So notice that the problem is exactly the same as the one that we did, but now everything is swapped. So now the volume itself is oriented on the y-axis. So now the whole volume is going to be in terms of y, okay? Or x, at least the inner function will be y equals something, okay, in terms of x and z. And now the other two variables that weren't used is going to be what our region is going to be as, okay? So let's distribute this r. So we're going to have the integral from 0 to 2 pi, the integral from 0 to 2, 3r minus r squared sine theta, dr d theta. And now what we're going to do, we're going to take the double integral, okay, or the first integral. So we're going to have 0 to 2 pi. This guy is going to be r squared over 2, so it's going to be 3 halves r squared. The other guy is going to be r cubed over 3 sine of theta. This is going to be from 0 to 2 of d theta. So now I'm going to plug in the 2. So I'm going to have 2 squared, which gives me 4. 4 times 3 gives me 12, divided by 2 gives me 6. So the first guy is going to give me 6 when I plug in the 2. We get 6 minus, then I'm going to plug in the 2 in there. So I'm going to have 2 cubed, that's going to give me 8 over 3 sine theta. And notice that when I plug in the 0, it's just going to give me a big fat 0. So nothing's going to happen. So I'm just going to have a minus 0. Okay, so now all I'm going to have to do is just integrate now with respect to theta. So integrating this, you're going to have 6 theta minus 8 over 3. The integral of sine is going to be negative cosine. So now this turns into a positive sine. And now I'm going to integrate from 0 to 2 pi. So I'm going to have 6 times 2 pi plus 8 over 3 cosine of 2 pi minus 6 times 0 plus 8 over 3 cosine of 0. So what I'm going to end up with, this guy's going to give me 12 pi. Cosine of 2 pi gives me 1, so you're just left with 8/3. This is going to give me a 0 minus cosine of 0 is 1 times 8 over 3. It gives me another 8 over 3. You can see that the 8 over 3's cancel out, and I get a volume of 12 pi. So the volume bounded by that plane and that cylinder is going to be equal to 12 pi units cubed.